This is the electrostatics topic, and this section is 7.2, dealing with the law of conservation of charge. Now, there are many conservation laws in nature. In physics, we talk about the law of conservation of matter or mass. We talk about the law of conservation of energy, the law of conservation of momentum. Now, these laws are all basically related in that they're all, to a large extent, saying the same thing about different parameters that we study in physics. Now, go back to 3rd grade or maybe 6th grade or maybe 8th grade, and I know you heard the law of conservation of mass or matter, the law of conservation of mass or the law of conservation of matter. And it went something like this. Matter cannot be created or destroyed, only changed from one form to another. Well, if you can't create matter and you can't destroy matter, then doesn't that just mean that the amount of matter that you have at the beginning is equal to the amount of matter that you have at the end of some process or some event? So, the first thing that I'd like to talk about in this section about the law of conservation of charge is how all of the conservation laws, including the law of conservation of charge, are related in that they're all basically saying that the total at the beginning equals the total at the end of some process or event. Here we go. So, there are many, many conservation laws in science. When you took chemistry, you had the law of conservation of matter or mass. And the reason that you balanced a chemical equation was to make sure that every single atom that was at the beginning of the equation had the same exact number of atoms at the end of the equation. So if there were 4 hydrogen atoms at the beginning, there had to be 4 hydrogen atoms at the end. And if there were 6 oxygen atoms at the beginning, there had to be 6 oxygen atoms at the end, etc., etc., etc. Not a single atom in a regular chemical reaction is created or destroyed. In other words, the total matter at the beginning of a chemical reaction is equal to the total matter at the end of the chemical reaction. Now that you're taking physics, we have the law of conservation of energy. Back in 3rd grade, we said energy cannot be created or destroyed, only converted from one form to another. What we say now is that the total energy at the beginning of an event is equal to the total energy at the end of the event. In other words, none of the energy is created or destroyed. Now, there is a special circumstance of the law of conservation of energy, and that would be when the system is frictionless. When the system is frictionless and no heat is generated, then we say that we have the law of conservation of mechanical energy instead. So again, when the system is frictionless and no heat is being generated, in other words, the heat is not bleeding off into the air, then what we have is the law of conservation of mechanical energy. Now, you can find the law of conservation of energy in the work energy and power topic, and you can find the law of conservation of mechanical energy in the work energy and power topic. Now, the law of conservation of mass and energy together is necessary when we talk about nuclear reactions. Back around the early 1900s, scientists were starting to do nuclear reactions. They were starting to observe alpha decay and beta decay and the changing of one element into another element, otherwise known as transmutation. And what was happening is they were measuring the amount of mass at the beginning and finding that at the end there was a little bit of mass missing. Well, what was happening was that some of that mass was being converted to energy. So what they had to do was they had to say, okay, since matter can be converted to energy and energy can be converted to matter, and by the way, here's the equation that does that, all right, your favorite and mine, E equals mc squared, all right? Since energy can be converted to matter and matter can be converted to energy, then what you need is a law that says the law of conservation of mass and energy together, which says mass and energy, the total mass and energy present at the beginning of an event is equal to the total mass and energy present at the end of the event. And again, you can find this discussion of the law of conservation of mass and energy in the modern physics topic. In momentum and impulse, we have the law of conservation of momentum. And again, it has to be a frictionless system for the law of conservation of momentum to be upheld. But again, the total momentum at the beginning of an event is equal to the total momentum at the end of the event. Which brings me to the topic of this section, and that is the law of conservation of charge. And you guessed it, the law of conservation of charge states that the total charge at the beginning of an event is equal to the total charge at the end of the event. Now, all of these laws also assume that the system that you are studying is closed. And basically that's saying that nothing can enter or leave the system. So, if you'd like to copy the law of conservation of charge, you can copy it now. You can pause the video. Here we go. In an isolated system, and that would be a closed system, the asterisk at the bottom tells us that a closed system is one in which no charge can enter or leave the system. We say charge because we're talking about the law of conservation of charge. In an isolated system, the total charge at the beginning of some event equals the total charge at the end of the event. Now, another way to say that would be, in an isolated system, the total charge remains constant. Now, keep in mind that a synonym for total charge would be net charge. If you see the word net charge, think of it as total charge. In a moment, I'm going to be talking about how electrons can be transferred from one object to another. Here's a piece of fur, and when you rub the fur with a piece of rubber, a rubber rod, electrons come off the fur and go onto the rod. We say that electrons are transferred from the fur to the rod. But what I'd like to talk about for just a few minutes first is why only electrons are transferred. In this whole topic, electrostatics, electrons are being transferred. Protons are never transferred. They're never moved from one object to another. Now, the explanation, the simple explanation would be, if you think back to chemistry, let's take, for example, an atom of lithium. There's atomic number 3 and mass number 7. So we know from the 3 on the bottom that lithium has 3 protons. Every lithium atom has 3 protons and 3 electrons. Now, that makes the atom neutral. The 3 pluses are exactly canceled by the 3 minuses. Now, if you subtract, we find that lithium also has 4 neutrons. So 4 neutrons. So now if we construct a lithium atom, then what you'll find is that your protons, now we'll make the protons these these small yellow ones. The neutrons will be the large yellow ones. So we need 3 protons, 1, 2, 3, in the nucleus. All right, and we need 4 neutrons, 1, 2, 3, and we put them tightly together because that's the way they are in the nucleus, very, very tight. All right, 1, 2, 3, 4 neutrons. So there's my 1, let's see that one. All right, stay there. 1, 2, 3 protons and 1, 2, 3, 4 neutrons, packed tightly in the nucleus and held together by the strongest of the 4 fundamental forces, the strong nuclear force. So those protons are not going anywhere. If you were to start busting up the nucleus, you would have a very tiny atomic bomb, right, in my little discussion here, and I don't want that to happen. That would be bad, all right? So again, we're not busting up the nucleus. The protons and neutrons are held together by the strongest of the 4 fundamental forces, the strong nuclear force. So now let's put the electrons around the nucleus in shells. All right, so let's erase some of this so we have room. All right, we don't need that either anymore. All All right, and we'll use the old Bohr model, the orbital model. The model that has orbits. Even though this is outdated, it's a nice way to show what's happening here. All right, in a very simple way. Okay, you know from chemistry that we don't put the electrons in specific orbits like that anymore. All right, but for purposes of this simple little discussion, all right, the electrons are now, all right, around the nucleus, and there's the same number of electrons and protons. 1, 2, 3 electrons. 2 in the first shell and 1 in the second shell. All right, so now, in the simplest explanation, it is very, very easy for an electron, you just pull it off the edge, an electron to be removed or to put the electron back. All right, it's easy to lose an electron, it's easy to gain an electron because they're on the outside, right? And the force, the electrostatic force that's holding the electron to the protons is not as strong as the strong nuclear force that's holding the protons and neutrons together. So, only electrons can be lost, all right, all right, and only electrons can be gained. We'll put them back, all right, in their orbit. Okay? So the protons, 1, 2, 3, are not going anywhere. You can't reach in there and pull them out. They're just not budging because of the strong nuclear force. Now, we're about to start a discussion about what happens to the charge on an object when electrons are transferred from one object to another. Now, I'm going to start with these two objects being neutral. The fur is neutral, the rod is neutral. Now, when an object is neutral, it has the same number of pluses. These are the protons. They're positive, 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 positive. All right, let's say that there's 6 of them. And again, we're dealing with tiny little numbers here, right? And we can't even really say how many atoms this piece of fur has. It's billions of trillions of quadrillions of quintillions of sextillions. All right, but let's just say we've got 1, 2, 3, 4, 5, 6 pluses, 6 protons. And we've got 1, 2, if the object is neutral, we have the same number of electrons. So there's your 6 electrons. The fur is neutral, all right? It has the same number of pluses and minuses, all right? So we'll put that over here, all right? Now, the rod is also neutral. All right, let's give the rod 4 pluses, all right? 1, 2, 3, 4, and give the rod 4 minuses. The rod is, all right, the rod is neutral, okay? And we'll even give him 7. All right, so now the fur has 7, the rod has 4. All right, now, this is the fur. It's neutral. It has the same number of pluses, 1, 2, 3, 4, 5, 6, 7 pluses, and 1, 2, 3, 4, 5, 6, 7 minuses. The rod over here, all right, is neutral. It has the same number of pluses, 1, 2, 3, 4 pluses, 1, 2, 3, 4 minuses. All right? Now, when we rub the rod on the fur, electrons are transferred from the fur to the rod. All right, so let's give the rod 3 electrons that came from the fur. All right, so what we see now is that the charge on the fur is, now here's neutral, neutral, right, plus minus, that's neutral, that's 0, neutral, 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 but now the fur, all right, now the fur has a charge of positive 3. All right, and I'll say positive 3 elementary charges, or positive 3e. The rod is now 1, 2, 3. It has 3 negative charges. All right? So, I mean, this is neutral, this is neutral, this is neutral, this is neutral. We can forget about those. All right? But it has 1, 2, 3 extra negatives. All right? So you see that when the fur transfers electrons to the rod, the fur becomes positively charged, and the rod becomes negatively charged. And again, this all happens by electrons moving. Only electrons are moving. So now let's look at what happens again when electrons are transferred from one object to the other. We have the fur, we have the rod. All right. Now, what I'd like to do is draw a picture of the fur. All right, here's the fur, and a picture of the rod. All right, here's the rod. And usually they put a tip on the rod so that if you touch another object, the electrons are kind of going to be directed right toward that tip and concentrated at the tip. So that's why the rods generally have a pointy end. All right, so there's the fur and there's the rod. Now, if you remember, we said, and you have no way of knowing which way the electrons are going to go. Are they going to go from the fur to the rod, from the rod to the fur, unless somebody tells you what direction they go. Right? In the case of fur and rod, the electrons always go from the fur to the rod. The fur becomes positive, the rod becomes negative. Now, we said that the electrons are being transferred from the fur to the rod. Now, what if 5 electrons are transferred from the fur to the rod? Right now, I want to remind you before I erase this that electrons are negative, okay? Losing electrons, you are losing negatives. Gaining electrons, you are gaining negatives, all right? Now, let's just say, and again, this number is not real. This number is very, very small. We're using small numbers so that we can understand that we'll go to bigger real numbers later on. Now, let's say that the fur, all right, the fur lost 5 electrons. So now the charge on the fur is positive 5e. All right, and let's say that the rod gained 5 electrons, so that the charge on the rod is now negative 5e. Now remember, that's because they were both neutral to start with. Now, what we'd like to know is what is the charge on the fur and the rod in coulombs, right? And there is a way to figure that out. All right, knowing the charge on one electron, all right, we can figure that out. Now I'm going to show you 2 different ways to actually figure that out. So let's do the fur first. All right. So what we're doing now is 2 ways to calculate the charge on an object in coulombs. All right, 2 ways to calculate the charge on an object in coulombs. All right, now we're going to have, you can copy that down, because I'm going to erase that right away. All right. We're going to have the factor label method, which you've seen before. All right. So now, if you have positive 5e, all right, then, all right, and E standing for elementary charge, the charge on a proton or an electron, all right. What we do is we want to get rid of E, so we put E down here. So, and we want coulombs, so we put coulombs on top. So the E's are going to cancel. And these 2 here must equal each other. So 1E is equal to, now for positive, this is going to be positive 1.6 times 10 to the negative 19 coulombs. All right, so if you now multiply 5 times 1.6 times 10 to the negative 19 coulombs, the charge on the fur, the actual charge on the fur, since it's positive 5e, the charge on the fur is positive 8. In other words, you're multiplying 5 times 1.6 times 10 to the negative 19. Positive 8 times 10 to the negative 19 coulombs. Now, there is another way to do this. and we're going to call this, all right, the total charge equation. And it's just a little bitty equation that we sort of kind of made up, all right? So, charge total, all right, is going to be equal to the number, n, the number of electrons or protons, all right, number of electrons or protons, all right, times E, and E standing for elementary charge. All right, so if you keep this little equation in mind, take the number of electrons or protons, multiply it by the elementary charge, you're going to get the total charge. All right, so I'm going to do that now. All right, so we have 5. Let's say in the case of the fur, it's plus 5, because we've got 5 extra protons in the center. All right, we lost 5 electrons, so what we actually have are 5 extra protons. That's why it's positively charged. The electrons that would normally be canceling this are missing. They were lost. So we've got 5 protons. The elementary charge, positive 1.6 times 10 to the negative 19 coulombs. All right? And the total charge, Q total, that we get is positive 8 times 10 to the negative 19 coulombs. All right, so it doesn't matter if you use the factor label method, all right, where one elementary charge is 1.6 times 10 to the negative 19 coulombs, or use this little equation, all right, where again, one elementary charge is 1.6 times 10 to the negative 19 coulombs. All right, it doesn't really matter. You can think of it either way, okay? But what we figured out is that the charge on the fur is positive 8 times 10 to the negative 19 coulombs. All right, now, we're getting to the part where we show how this is all related to the law of conservation of charge. Now, I do have to say this, all right? When you rub the fur and the rod together, the fur becomes positive 5e, that's positive 8 times 10 to the negative 19 coulombs. The rod becomes negative 5e. That's negative 8 times 10 to the negative 19 coulombs. All right, so the 5 electrons that left the fur and made it positive are now on the rod, making it negative. Well, if this lost 5, it's 8 times 10 to the negative 19. Whatever this guy lost, this guy gained, and that's why he's negative 8 times 10 to the negative 19. All right, now, let's see how all of this proves the law of conservation of charge. All right, so now we'd like to prove the law of conservation of charge. The total charge at the beginning is equal to the total charge at the end. Now, if you remember, at the beginning, the fur was neutral and the rod was neutral. All right, so at the beginning, let's say charge on fur plus charge on rod, all right, was 0 coulombs and 0 coulombs. So at the beginning, the total charge is 0 coulombs. Now, what about at the end? All right, at the end, the charge on the fur, at the end, all right, this little prime up here generally means after, all right, and the charge on the rod after, okay? The charge on the fur after the electrons moved from the fur to the rod was positive. If 5 electrons moved, then the fur is positive 8 times 10 to the negative 19 coulombs. And if those electrons moved to the rod, then the rod is now negative 8 times 10 to the negative 19 coulombs. So we add those two together, and what's the total charge at the end? The total charge at the end is 0 coulombs. All right? So very, very simply, this simple little demonstration, all right? The fur is neutral, the rod is neutral. I rub them together, and if the electrons that leave the fur are now on the rod, all right, then the fur and the rod together are still neutral. All right, so the law of conservation of charge is upheld. The total charge at the beginning, before an event, before the rubbing them together event, all right, is equal to the total charge at the end. All right, so far, the law of conservation of charge is doing just fine. What I'd like to do now is a similar problem, but with a more realistic number of electrons. So what I have here is a piece of clear acetate, it's a type of plastic, and a piece of paper. And when you rub acetate on paper, the acetate loses electrons and the paper gains electrons. So let's say, for example, that when I rub these together, and let's say that they start out neutral, all right, and when I rub them together, let's say that the acetate loses 650,000, all right, electrons. So the acetate is now positive 650,000 times the elementary charge, all right, in positive elementary charges, all right, and the paper, all right, is now negative 650,000 elementary charges. So again, here's the acetate, all right, here's the paper, and the electrons are being transferred from the acetate to the paper. So the acetate becomes positive, all right, 650,000, all right, elementary charges, and the paper becomes negative 650,000 elementary charges. All right, so let's calculate the charge on the acetate and the charge on the paper. All right, so, and remember, the numbers, the magnitudes are the same because every electron that leaves the acetate goes to the paper. If it was 3, it would be positive 3, negative 3, because they both started out neutral. All right, so 650,000 E, all right? How much is that in coulombs? Well, 1 E, and this is positive, would be positive 1.6 times 10 to the negative 19 coulombs. All right, now if you multiply that number times that number, let's just double check the math here. All right, so 650,000 times 1.6, all right, 10 to the negative 19, we're getting positive 1.04 times 10 to the negative 13 coulombs. All right, so that's the exact charge on the acetate after you rub it with the paper. Now the paper, all right, and let's do this the other way first. All right, so this is the factor label method. All right, let's do the little equation. All right, the total charge is going to be equal to the number of electrons that were lost or gained, all right, times the elementary charge. All right, the number of electrons that were lost or gained is 650,000. Now, why don't we convert that to scientific notation? Instead of 650,000, we're going to do 1, 2, 3, 4, 5 places. So that would be 6.5 times 10 to the 1, 2, 3, 4, 5 to the 5th. All right, that's how many, it's a number, that's how many electrons were lost. And the elementary charge, we're going to make it positive because we know that the acetate is positive because these electrons were lost, all right, to the negative 19 coulombs. All right? Now, technically, this is 6.5 times 10 to the 5th, all right, electrons, right? And this is 1.6 times 10 to the negative 19 coulombs per electron. So what's actually canceling out is the electrons. But in any case, you're going to get how many coulombs. And if you multiply this number times that number, again, you're going to get 1.04 times 10 to the negative 13 coulombs. Now, make sure that it works out that your answer is positive because you know that the acetate became positively charged. All right? And again, whatever charge was left the acetate went onto the paper. So if the acetate right now has a charge of positive 1.04 times 10 to the negative 13, then the paper must be negative 1.04 times 10 to the negative 13. So at the beginning, all right, the charge on the acetate, that's a kind of clear plastic, and the charge on the paper were both 0 coulombs and 0 coulombs. All right, at the end, the charge on the acetate, all right, after rubbing, the charge on the paper, after rubbing, the little prime means after, the charge on the acetate after rubbing was positive 1.04 times 10 to the negative 13 coulombs. The charge on the paper was negative 1.04 times 10 to the negative 13 coulombs. All right, so again, the law of conservation of charge is upheld. The total charge at the beginning is 0 coulombs, and the total charge at the end is positive 1.04 plus negative 1.04, etc., etc. The exponents are the same, so the charge at the end is 0 coulombs. All right? The total charge at the beginning, before an event occurs, the rubbing of the acetate with the paper event, all right, is equal to the total charge at the end.